Hey, I'm Mart Bassey, and today I'd like to talk to you a little bit about how Rust embedded works on the microbit, namely the very basics of microcontrollers and electricity and all the things that we need to understand how to do a very simple thing in Rust. And so we're going to do this in the context of what I call the hello world of Rust, which is of Rust embedded, which is blinking an LED on the board. So let's start by looking a little bit at the microbit, what it actually is. So let's look first at the microbit itself for a minute. Um, this is our BBC microbit, and again, here on the front is LEDs, among other things. There's a 5x5 array of lamps, light emitting diodes, actually, that can put out light in response to electricity. And again, on the back of the board, we have a whole bunch of circuitry. One piece of which is this guy right here, this little black guy rectangle right here, which is actually your microcontroller. It's actually the thing that actually makes everything go. And so how this works is this USB cable we got plugged in on top up here provides plus 5 volts on one wire and accepts electricity on the other wire. We call that a ground wire. So this connection of plus 5 volts to the circuitry to ground is what we call a circuit. Electricity flows out of the USB cable through all this electronics and then back into the USB cable. The USB cables supplies 5 volts. Volts is a measure of how hard the electricity is pushed, and this electricity is pushed 5 volts worth. The first thing that happens as the electricity comes in is a circuit called a voltage regulator converts that 5 volt push down to a 3.3 volt push because all the internal electronics of the microbit use 3.3 volts as their required voltage. So now we've got this electrical supply, and part of what that electrical supply is connected to is power supply pins on the microcontroller. That little black rectangle there has 2 copper wires running through this fiberglass printed circuit board. This is just made out of fiberglass with little electrical wires called traces inside. There's a wire that runs from here to the voltage regulator and from the voltage regulator over to this microcontroller, and that supplies electricity. There's also a ground wire that runs back to the USB cable from the microcontroller that takes the electricity away when you're done with it. The amount of electricity flowing through a circuit is called the current. So voltage is how hard the electricity is pushed. Current is the amount of electricity that's going through. And what's going to happen is the microcontroller is going to route some of that energy, some of that electricity into other things. In particular, there are wires going from the microcontroller to each of these LEDs and from each LED back to the microcontroller. That's a power and ground wire for the LED. What we can actually see if we look at a circuit diagram for this, let me show you what's called a schematic. And a schematic is a kind of circuit diagram that shows you how all the wires are connected. So let's go grab that. This is the microbit schematic. It is linked from the repo. The microbit schematic, if you look at the whole thing, has a whole bunch of pieces, but we'll be concentrating for now on the LEDs, which are right here. That funny little arrow with a bar here is the symbol for a lamp for a light emitting diode. The little arrows coming out represent light coming out. And if I put a voltage here and put ground here, then electricity will flow through this light emitting diode and it will emit light. That's how we turn it on. These black things here are wires. Those are the things that actually show are sort of the symbolic equivalent of electrical wires. Row 1 is connected to one side of this LED. Column 1 is connected to the other side. These things aren't connected because there's no dot there, so don't get confused. The point is that electricity is going to flow from the row 1 place through the LED and then out the call 1 place. This thing right here is called a resistor, and it keeps it from flowing too fast and burning up the LED. So our job is to turn the row, put a voltage on the row 1, put 3.3 volts on the row 1 wire here, and then put ground on the call 1 wire, and that'll be our first job, is to turn on the LED. Now to do that, what we're going to do is we're going to go down here and look at the actual microcontroller itself. And what we see is that this row 1 thing is actually wired directly to the microcontroller at a place called P0.21 internally. I'll explain that in a second. Down here, call 1 is P0.28. So what we need to do is make the microcontroller make P0.21 be plus 3.3 volts, make P0.28 be 0 volts, and we should get a light turned on. So how do I do that? Well, that requires the second document we're going to look at today, which is our microcontroller manual. This document here is our microcontroller is called the NRF 52833. It's made by Nordic Semiconductor. The RF part means that it's got a radio in it, which we will be ignoring, but it's there. But the Nordic 52833 is a fairly standard microcontroller. What's a microcontroller? It's got a little computer on the chip, and it's got a whole bunch of devices that you can connect to that are connected to that computer, that you can connect to the pins on the chip to do things. In particular, we're interested in the general purpose I/O port, input output ports. So that's what GPIO stands for, is general purpose input output. These are just wires that you can use for things. And it turns out that there's sort of two sets of these GPIO wires that we call port 0 and port 1. Port 0 has 31 wires on it. Port 1 has another 10 wires on it. Sorry, 32 wires. And port 1 has another 10 wires on it. That's sort of a weird artifact of the architecture and not interesting. Both of our things, remember, were on port 0. So we'll only be playing with port 0 today. This right here is the address. So you got to understand a little about memory inside a computer. Inside a computer, the memory is organized into bytes, and each byte has a numerical location called its address. On the NRF, so what's memory? RAM is where you can store a value into the byte and then read it back later. Flash is where you can read bytes that have been put there by some mysterious process. These things are called device registers, and they're just memory locations that, instead of working like normal memory, do stuff when you read and write them. The memory locations starting at this address, which is just a big number that doesn't mean much, are memory locations that are used for turning the GPIO wires on and off. And we do that by a series of places you can read and write. So the 4 bytes starting at 504, for example, off of that address, so 5 bajillion 504, are a way to put output data to the GPIO port. These are the things we'll actually be using, which are a little special. We can get input data. So each of these wires we can either read or write from. Today we're going to be writing to them because we want to put electricity on them. And if you go to our wires here, you'll see to each of these ports, what you'll see is that at some offset is configuration registers for those ports. And then there's these output registers which cover all the 32 ports of pins of P0. And so this is a lot, and you don't necessarily need to understand it entirely, but you get the idea that basically what we're going to try to do is tell the microcontroller how to turn on a wire or make a wire accept electricity. So let's start by looking at these pin configuration registers. I think we wanted to look at the configuration register for pin 21. Come on. But you'll notice if you look that all the other pins here have the same registers. The only thing that's the same stuff, the only thing that's different is the address offset. So here at 5,754 is the pin configuration register for this. And the only bit in that 32-bit register that we have to worry about is this bit, the A bit. That's position 0 in the bits. And what that one is it says, are we going to read or write through this pin? And we want it to be 1 so we can write. And once we've set that up, and then we'll set the same thing up for pin 28, the other one. And once we've got these both set up to be writable, then we'll go back to this these outset and out clear registers and use those to actually change the thing from high to low or low to high. So here, if I put a 1-bit out somewhere in this outset register, so here's bit 21 of the register. If I write a 1 right here, then that will set pin 21 high. And if you go back to the out clear registers, assuming I can get there again, the out clear registers, it's basically the exact opposite. When we write a 1 into pin 28, then that will send the thing low, and that allows it to accept electricity. So this is the first thing we have to do is configure the pins. The second thing we have to do is actually set 21 to high and 28 to low, and we'll be all good. We'll be all in business here. So I'm going to skip way ahead, and we're going to look at some terrible Rust code for doing this. And this is not the way I recommend that you do this. It's just the way that I'm going to show you how to do it, so that you understand the basics of what's going on. So let's oops. So let's look at some Rust code that actually does the thing I said. And we'll look at the code first, and then we'll go back and look at how to build it and run it. Well, first of all, let's look at a simpler program. This thing just turns off the light. I'll explain later why we need that, but it's a little simpler program that's easier to understand. Let's skip all this glop for just a second. I will come back to it. This is the thing we read about in the manual. This is the address that the GPIO registers are located at, and this is the P0 registers, which are right at the GPIO base address. Notice this is a Rust constant declaration. It says there's a constant called named GPIO base, which is of type usize, which in this case is 32-bit unsigned integer, and has this value. By the way, it's common when writing hex numbers to put an underbar here. Rust ignores those underbars, but it does make things a little bit easier to read. I'm going to undo that for now, though. This is that offset we read about in the manual for the block of pin configuration registers. And we know that the row 1 pin is connected GPIO port 0 at position 21, and the call 1 pin is connected to GPIO port 0 at position 28. So now first we're going to configure these things to be writable, and to do that we're first going to make a pointer to a config pointer. We're going to have this variable store the address that we want to write into. And that's what this as pointer to mute U32 out on the end says. It says make this something we can write into. And then we're going to compute our address, right? Which is just the address of the row 1 port addresses and plus the GPIO, which is port 0 here, the GPIO config base, plus 4 times the pin number. The pin number here is 21. It turns out that if I go down to that, I'll be at the configuration address, and then I just make a pointer out of that. This unsafe here is a Rust thing that says, I'm going to be storing through a pointer and I don't know for sure what's going to happen. It becomes my job at that point to make sure I don't screw up. Normally with Rust, programs are safe. If you run a program, it'll either panic or complete with some answer. Here, you got to be really careful. You're responsible instead of the compiler being responsible that this write is going to be okay. But here we store the thing that says I want both these pins to be in input mode this time, not output mode, and disconnected, and that will turn off the light. So once we've got figured out where we want to configure this, we just configure it so the light's turned off. Notice this weird return type of exclamation point. The exclamation point return type here means this function will never return. Our main program can't return because normally it would return to an operating system, but we have no operating system. When we compile this program, it will be the only thing running on our computer. And so once we're done with what we came to do, we just sit here and spin forever. This is called no op for no operation. It means don't do anything, but explicitly don't do anything. That's a machine instruction for our computer. And so we just keep running that don't do anything instruction over and over, and we never return from the function. So that will turn the LED off. You'll have to trust me on this one. Let's go back up to some of that blop up at the top and talk a little bit about how we set this up. This just gives me access to the no-op instruction. I really wanted to be able to do that. This gives me a little decoration I can put on a function to mark it as the entry point or main function of my program. This one happens to be named main, but I could name it anything I want, honestly. Why do I need that? Because I told the compiler, don't use the standard library. That is, don't compile this Rust like normal Rust. We have a little tiny computer. It doesn't have room for all of the standard library Rust stuff. And so we're basically on our own at this point. We're not using any of Rust's machinery except the language itself. And the second thing says, there's no official main program. We'll provide our own entry point, which we do with that entry decoration down below. But in the meantime, we're like, yeah, no, don't treat this like an ordinary program. This is our first embedded program. And this use panic hold as underbar basically says execute the computer's halt instruction if anything goes wrong during execution. So that includes a library. Let's look at our configuration for this program. This thing says go to crates.io and download the Cortex MRT library at this version or later. The Panic Halt library at this version or later. And then the Cortex M library at this version or later, but with the cargo feature, which you don't have to worry about right now, of allowing inline assembly like we were using earlier. So this tells Rust how to compile the Rust cargo, the build tool, how to build your program. Notice that the edition here is 2024. That means use the latest language features of Rust. That will be supplied by default by Cargo New. The other thing we should look at is this horrible piece of horribleness, which is, if you look, there's a directory called .cargo here, and if we look in it, we'll find config.toml. Let's go look at that. This thing says, when you build the program, our program, Rust compiler, please build it for this kind of machine. This is the instruction set of our microbits computer, which is different than the instruction set of the computer I'm building on. And the rest of this is just more description of all that. And when we're building for that so-called target, use these, pass these flags to the Rust compiler, which makes it build properly, and use this as the runner for that program. This when I say cargo run this command basically. So let's do all that just for grins. I'm gonna flip to our to where we can see what's going on. And we're gonna say cargo build dash dash release. You should usually use release mode to build embedded programs, because otherwise the bad thing will happen. They'll be big and bloated and slow. Really recommend this optimization. And this will take a moment while it downloads a whole bunch of crates from crates.io, compiles them, and builds our thing. And now in target the release is our executable program. It's a 70 kbyte executable program. That's but actually the program itself is only 1152 bytes, which is not bad. We have 512,000 bytes of program memory on our board, so this will fit quite handily. Now, how do we run it? Well, we really can just say cargo run release, and it'll run our command we said it should run earlier. And when I do that, whoops, pin off, because there's a couple binaries down there. And now it turned the LED off. Oh shoot, it was already off. Okay, let's do something cooler here. Is this working? It is, but I can't prove it to you yet. So let's go back and do something cooler for a moment. And you can see right here where it runs probars run dash dash blah. We can actually manually run that, and it will also run the program. But it's a little tedious to do, which is why we buried it somewhere. Notice that probars hangs after it starts. That's for a good reason we won't talk about, but it doesn't need to. The program's still running even though I stopped probars. So that probars command actually finds my microcontroller board where it's hooked to the computer and uploads the program through it and then starts it running. So let's look at a more interesting program here. This here is going to actually blink the LED, and you notice it starts exactly the same. There's not that much interesting stuff. The only thing we did is add the address offsets of our set a bit register, make a pin positive, and our clear a bit register, which makes a pin ground. And so here we're going to basically start the same way. We'll come back to this delay in a second. We're going to set up the row and column configuration. We're going to also set up pointers to these set and clear registers. We're going to be able to both set or clear row 1. We'll also set or clear call 1. And this is just the same kind of address calculation we were doing before. And now we're going to start by making things output mode this time. Instead of disconnecting those pins, we're going to connect them as outputs. And then we're going to take the call one pin and make it sync current. And we do that by this bitwise shift left of a 1 to the right place for the column 1 pin. And then we write that through this pointer. That's all we need to do. Notice this is all unsafe because we're writing through pointers a bunch of places. Then we do this loop. This time our loop actually does something. It doesn't just spin meaninglessly. What we actually do is we turn on the row 1 pin, and then we wait a bit, and then we turn on the column 1 pin. Sorry, clear the row 1 pin, my bad. We turn on the row 1 pin, then we clear the row 1 pin. We set output to 0, meaning it will accept current now. It's not doing anything. And then we spin again. So during this time, the LED should be on. And during this time, after this, the LED should be off. And this delay in the middle is super stupid. It just sits there and runs 4 million cycles of just sitting and running no op instructions. Notice that no op has to be explicit. If I just wrote this, the compiler would optimize away that loop. It's like, well, yeah, you said to do something 4 million times, but since there's nothing to do, I won't bother. Here I give it something it has to do 4 million times, and so it will actually wait. On our processor, which if I remember right is it 64 megahertz or 80 megahertz? I can't remember. It's very fast, a bunch of million instructions a second. This will give us about a half second. That comment is wrong. This will give us about a half second delay. So yeah. So we're gonna turn the light on, delay for a half second, turn the light off, delay for a half second, and then we're gonna do it all again. And that's what we're gonna get. So again, let me demonstrate that. We will okay, and you'll notice the minute it starts running, it blinks on and off once a second. We call that the hello world of embedded because it shows that I can control the microcontroller board enough to be able to manipulate a pin and to control time a little bit. And so this demonstrates we're ready to do more interesting things. What if your microcontroller board is not a microbit and doesn't have an LED? Well, that's a trick question. Every microcontroller board has an LED. So I said before, and I can prove it now, when I stop ProBarS, nothing interesting happens. ProBarS was not, once it uploaded your program and started it running, it runs by itself. And you say, well, I want to stop it from running, so I'll just do what you always do with computers, and I'll turn it off and then turn it back on again. Oops. When I turn it back on again, it starts blinking. Why? Well, because our program is now stored in memory on the microcontroller that survives even across power outages. So if I turn the power off and on, or if I push the reset button, which is on the back of this thing, it just starts right up again doing what it was doing before. Well, how do I turn it off? Well, we had a program for that, and that's why it was there, is I want to run this off program. So remember I said I couldn't prove to you it works? Well, now it does. Now, every time I restart this thing, I power it off and on again, or I reset it, it will run the off program again, and that LED will stay off. So that's super low level. It's not the way we will program ever again. All those numbers and weird pointers and all that stuff are not the way you should use Rust. If you want to program like that, I highly recommend the C programming language, which is, this is how you would write this in C. It's probably not going to be much prettier than this. But we can do better than this. And in the next lesson, I will take you through what good Rust programs for blinking this LED look like at a number of levels of abstraction. This is what we call sort of raw IO, and we'll do better than that going forward. So I hope this was useful for you. Look forward to talking to you again soon.